Okay, we can use linear transformations to stretch space. Okay, we saw that very early in the course where we had the problem of looking at a circle in R2 and then applying a transformation that distorted the circle into an ellipse. So we take the circle, we could pull it this way, and then we can pull it this way, or even compress it this way, okay? And by pulling and compressing in two different directions, we deform the circle into an ellipse, and that it has the effect of distorting space, or distorting the plane. In three-dimensional space, we can pull in three independent directions, or compress. Okay, so we pull in this direction, maybe make everything twice as long in this direction. We pull in this direction, make everything 3 times as long in this direction. And in this direction, maybe we make everything half as long. And that would take a sphere and compress it into an ellipsoid, okay, with the axes in this direction, this direction, this direction, and so forth. Other things we can do with space, of course, we can also rotate it without stretching it, okay? And then we can combine stretches and rotations, and that gives us a whole huge group of transformations, and group has a kind of a specific mathematical meaning. Okay, so what I want to do is I want to see if this particular matrix does any of that stretching, okay? Now, if it stretches in some direction, that means it takes any vector in this direction and transforms it into a vector in the same direction, but longer or shorter, okay? Which means if the x is such a vector, that a times x is going to be some multiple of x. It's going to be in the same direction as x. Of course, it could also flip it backwards, okay, but we'll take that as a stretch as well, okay? At least for right now. We want to refine that a little bit. But a times x equals some multiple of x. This is a statement that says that the vector x is transformed to another vector along the same line, but perhaps of different length, okay? And of course, any vector can transform to the zero vector. So if lambda is 0, well, that doesn't give us any information. So lambda, we don't want to be 0, okay? Well, that's the condition of a stretch in a certain direction of space. Okay, so ax then equals lambda x. Well, x is the same thing as I times x. Identity matrix times x, it's still x. And you'll see why we're making this substitution. Okay, so I rewrite this in this form, and then I subtract this from both sides to get this. Okay, now having done that, well, lambda times ix by rules I hope that we've proven and understand is the same as lambda I multiplied by x. Okay, so the left-hand side becomes this, and then if I simply factor out x, which I can by the linearity of matrix multiplication, I get a minus lambda I times x equals 0. Okay? Now, if a minus lambda I is invertible, it follows that x equals the inverse of a minus lambda I times the 0 vector, and that's the 0 vector. And that's not of any interest. Uninteresting. It doesn't give us a direction. The 0 vector doesn't have a direction. If this happens, we don't have a direction in space. We just got a point. Okay? So, the interesting case occurs when this isn't invertible. Now, if a minus lambda I isn't invertible, that means its determinant is 0. So our condition for an interesting situation is that this determinant be 0. Okay? So let's go back to our given matrix A. Okay, well, a minus lambda I is, well, here's our A, and here is lambda times the identity matrix. And of course, it's got to be a 2 by 2 matrix, or we don't have addition, so that's implicit. So we have this, and of course this minus this is this. So our condition is that the determinant of A minus lambda I, which is the determinant of this matrix here, has to be 0. Okay, well, the determinant of this matrix is very easily calculated. You're going to have the product of these diagonals, 2 minus lambda times 3 minus lambda, minus the product on this diagonal, which is minus 2, giving us lambda squared minus 5 lambda plus 4. Now that determinant, in order to make the problem interesting, has to be 0, so the determinant of this is 0. The determinant of A minus lambda I is 0 if and only if this quadratic polynomial in lambda is equal to 0. Well, we can determine whether this has a solution, and if it does, we can determine what it is, because this is nothing but a quadratic equation. And we even have a formula that we can use to solve that if necessary. Now in this case, this thing is very, very easily factored, so we don't need to resort to the quadratic formula. Since we can factor it over the real numbers, we know that it has a solution. So the solution is lambda equals 1 or lambda equals 4. Now, maybe if we didn't see to factor that, we would at least check out the discriminant to see if we have solutions. Okay, the discriminant's your b squared minus 4ac, that thing you take the square root of, and b squared would be negative 5 quantity squared, which is 25. In 4ac, a is a coefficient of lambda squared, c is the number you have over here. That's just going to be 4 times 4, which is 16. Okay? So you're going to have 25 minus 16. And something's haywire in that, but I'm not going to mess with it. Okay? Never mind. It's okay. It's okay. I forgot you have the denominator too. These were going to be too close together. If I had a square root, a discriminant that was equal to the square root of 9, which is 3, but just, brain lapse there on my part. Okay, so anyhow, you would check out the discriminant. If the discriminant is 0, that means you have a repeated real root. If the discriminant is negative, that means you don't have real valued solutions. Now, complex valued solutions in the context of complex vector spaces over complex numbers, very profound and a little more advanced than we're going to be in this course, but we're going to be right on the cusp of it. Okay, well, anyhow, so if lambda equals 1, okay, lambda's 1 or lambda's 4, and we can test the discriminant and do all that stuff. But we should understand quadratic equations well enough that we know exactly what to do. If not, review it. Okay, if lambda equals 1, because that's one of our possible values, then this equation a minus lambda I times x equals 0 becomes this, okay? And of course that is what this equation becomes, right? So this equation for lambda equals 1 becomes this, okay? Because this equation is the same as this equation, and a minus lambda I is this, so that this would equal 0. So that, and lambda is 1, so 2 minus 1 is 1, so you get 1, okay? And that's really what it comes down to. We come down to this matrix. This is your a minus lambda I matrix. If lambda is 1, you get 1 here, and you get 2 here. Okay, and of course you still have the 2 and the 1 here. Okay, so your equation a minus lambda I times x equals 0 becomes this. And then if we write that out as 2 equations, we see that 2 equations are the same. And it's always going to be that way for a 2 by 2 matrix when you find an eigenvalue. The equation might not be identical, but they'll be multiples of one another. So any solution to the first is a solution to the second. So this will just reduce down to a single equation. So the equation here could be x1 equals, have solution x1 equals negative x2. You have a free variable, let x2 be your free variable, and you have solution negative 2t, or t times negative 2, 1. Okay? So negative 2, 1 is what you would call your eigenvector, and your eigenvalue is 1. Now, check my time here, we're doing okay. Get a good color here. So what we've determined here, for lambda equals 1, the eigenvalue lambda equals 1 implies that the negative 2, 1 is I'll say a corresponding eigenvector. That would be an eigenvector that has eigenvalue 1, meaning that negative 2, 1 is a vector such that A times that vector is lambda, the eigenvalue 1, times negative 2, 1. Okay? And you can check that out. Now, if lambda is 4, very straightforward. This matrix becomes 2 minus 4, which is negative 2, 3 minus 4, which is negative 1. And, of course, you still have the 2 and the 1, so that this equation, this equation here, which is totally equivalent to this equation, becomes this matrix times x equals 0, giving us, again, 2 equations. And you can see that the second equation is not identical to the first, but it's, if you multiply the first row by negative 1/2, you get the second row, so the second equation is a multiple of the first. And either equation is going to give you a solution that you can find easily. x1 has to equal x2, so that x is s times 1, 1, some multiple of 1, 1. Okay, so say this, 1, 1 is an eigenvector with eigenvalue 4. Meaning if you plug any multiple of 1, 1 in here, you're going to get a vector that's in the same direction but 4 times as long.